Okay, welcome back. Now, here are the steps. I'm going to explain the steps to you as we're doing this, okay? So, these are the problem-solving steps in a nutshell, and I'm going to explain each one. So, it's really simple. You start by, basically what you're going to do is you're going to check all three conditions. So, you start with condition number 1, and you check to see if f of a is defined. If f of a is not defined, then you're done. We know that it's discontinuous at the point. If f of a is defined, then go to the next step. Check the next condition, which would be condition number 2. So in condition number 2, you're going to compute the limit as x approaches that point A of the function f of x. Now, that might require you to check both the left side and the right side limits to see if they exist and to see if they are the same. Okay. That also might require you to do other things, right? And so the thing is if you compute the limit and the limit exists, meaning you get a real number, then you go on to the third condition. If you get something else, if it doesn't exist, or you get an infinite limit where there's an asymptote, let's say, okay, then that tells you that the limit is not a real number, therefore it fails number 2. Okay? And you're done. Then you know it's discontinuous. If it does satisfy condition 2, then go on to the final condition, which is then you compare the two. Right? You compare f of a and you compare the limit. If they are not the same, then you're done. You have a discontinuity at point A. If they are the same, then now you know, because you've satisfied all three conditions, that the function is continuous at the point A. Okay, so here's an example. So let's say we have this function here. Okay, now this is a function we've done before. We know that there's something going on at x equals 2. So we're going to go through the conditions and see if it satisfies all three conditions. If it violates or if it fails to satisfy any one of the conditions, we're done. Okay? So let's start with the first one. It says, check to see if f of a is defined. Well, what do? Well, we plug in 2 and see what we get. Well, right away, if we plug in 2, we get what? If we plug in 2, we get 0 over 0, right? Okay, so remember, this one we're going to have to factor, right? So we're going to factor the top because it's the difference of 2 squares. Oops. Okay? Now, before we go any further though, look at the fact that we get an indeterminate form, right? What does that tell us? Well, like I said, it tells us that there is something going on. Okay? So right away, we don't need to do this. Because remember, in this case here, when we do this, remember what I said before, when we're doing the factoring, we're removing the discontinuity. Why? Because in this case, we were dealing with limits, right? We were finding a limit. Well, we don't need to go there. That's step 2. We don't even need to go to step 2 because it fails here because we get 0 over 0, which tells us it's an indeterminate form, which means it's undefined. And so we're done. This is not continuous at x equals 2. Okay? But let's do another one. Okay? So let's do another example. Let's do this one. let's do a piecewise function. And this one's going to be f of x equal to negative x squared plus 4. And this is going to be for x is less than or equal to 3. And then, of course, we have 4x minus 8 for x greater than 3. And we're interested in what's going on at x equals 3. Okay, so now let's do condition number 1, right? So let's check to see if it's defined at a, at 3. So at 3, we're going to use this one. So if we plug in 3, what's f of 3? Is it defined? Well, we get negative 3 squared plus 4, which gives us a negative 5. So yes, it is defined at x equals 3. Okay, so now we can go on to the next one. Now we want to compute the limit. Okay, so it satisfied condition 1, so now we check condition 2. And this one is we're going to, the limit. We're going to evaluate the limit. So the limit as x approaches 3 of the piecewise function. Now in this case here, we're going to have to do the left side and the right side separately because we've got 2 rules. Okay? Okay, so let's do the limit from the left. And on the left side, we're going to be less than, right? The limit as x, now here's the thing, we can evaluate this. The limit from the left is going to be based on this rule, which means we're going to do negative x squared plus 4. Oops. Now we already saw that this limit here is going to be negative 5, right? Because we just plug in from our previous video, we found out that we can just plug in and evaluate by just plugging in the value of a. Okay, now let's do the limit from the positive side, the right side. And now we're going to do this rule, which is 4x minus 8. And now when we plug in 3 here, what do we get? Well, we get, 12 minus 8, which gives us 4. Okay, so that means because the left side and the right side do not give us the same limit, the limit doesn't exist, and it fails condition number 2, and we're done. So this is not continuous at x equals 3. Okay, now, okay, let's do another one. Let's do another example, and here we're going to have another piecewise function. So in this example, we're going to have f of x is equal to sine x over x for x not equal to 0, and 1 if x is equal to 0. Okay, and we want to know, is this continuous at x equal to 0? Is it continuous at x equals 0? Okay, let's start. Let's check the conditions. Okay, first, is it defined at 0? Well, yes. F of 0 is equal to 1. So yes, it satisfies condition 1. Okay, condition 2. The limit. So what's the limit as x approaches 0 of f of x? Well, again, we're going to have to do this from the right and the left. Well, actually, no, we don't have to do that from the left. We know, so at everything that's not equal to 0, right? This is the function. And we know that the limit as x approaches 0 of sine x over x is equal to what? 1. From our previous videos, previous discussion. So we know as x approaches 0, the limit of this function, sine x over x, is equal to 1. Okay. So far, so good. Okay. Now, the last thing is compare. Is f of a equal to the limit as x approaches a? Well, in this case, yes. F of 0 equals 1, which is equal to the limit as x approaches 0 of sine x over x. And so it satisfies all the conditions, and therefore this function f of x is continuous at x equals 0. That's it. Have a great day.